Welcome to Lecture 4 for Anatomy and Physiology, Diffusion, Osmosis, and Tonicity. Diffusion is going to be the continuous random movement of ions or molecules in a liquid or gas resulting in even distribution. Diffusion is primarily how we move things in the body, and it's a very useful concept. To have diffusion occur, we first need a concentration gradient. A concentration gradient is where there is a difference where some molecules are and some molecules are not. There's a difference in distribution. At even distribution, there's still molecular motion in a general compound, but no net movement from one area to the other. The movement of one area to the other is going to be diffusion. And it is slow in air and water, but this is very important over small distances. Giving you an example, here we drop a nice little cube of sugar into a compound, water, and we're going to see this gradually break down and diffuse as it goes from the high concentration of the sugar cube to the lower concentration, water, until it diffuses throughout and becomes equal. When discussing diffusion, there are 7 properties of diffusion and how it works in the body. 1. Diffusion is passive. That is, no energy from another source is necessary to make it happen. 2. Molecules move from high to low concentration. This is very useful, meaning that a larger gradient equals a faster rate of diffusion. So the rate of diffusion down the gradient depends on the magnitude of that gradient. The more of a compound there is, the more of a difference there is between those things, the faster it will diffuse. 3. Net diffusion continues until the concentration is equal everywhere. The key words there being net movement. Molecules will continue to move, but they have no particular directionality after the gradient is eliminated. 4. Rate of diffusion depends upon distance. The greater the distance, the more time it takes for molecules to move from point A to point B. The smaller the distance or shorter the distance, the faster the rate of diffusion. Here, diffusion time is proportional to the distance squared. 5. Rate of diffusion decreases as molecular weight or size increases. A smaller size of molecule equals a faster rate of diffusion, whereas a larger molecule is a larger rate of diffusion. Great example of this would be putting cream or milk, skim milk, in coffee. If I have 2 coffees and I put heavy cream in one and skim milk in the other, the skim milk will diffuse faster through the overall coffee than the heavy cream. 6. Rate of diffusion increases with temperature. Higher temperature equals a faster rate of diffusion. At higher temperatures, molecules move or vibrate more violently. That means that they have more potential energy so they can move faster. Lower temperature solutions are going to have slower diffusion. Great example of this is if I take that skim milk and I put it in hot coffee versus iced coffee. In the iced coffee, it will diffuse slower throughout the overall beverage, whereas in the hot coffee, it will diffuse faster. Finally, 7. Diffusion can occur in an open system or across a membrane. Now, this is very relevant to our discussion on membrane transport. Looking at diffusion across a membrane, we need to worry about permeability. Permeability is a property determining which substances can enter or leave the cytoplasm. Our cells are selectively permeable oftentimes. This means some substances can cross, others are prevented. The plasma membrane must allow some movement in and out of the cell to enable intracellular communication and coordination. These are 3 different examples looking at different permeabilities in cell membranes. First, we have a freely permeable membrane. This is where it lets everything in. It doesn't stop anything from coming in. We have proteins, lipids, ions, water, and carbs all moving through the cell membrane. On the flip side, the very bottom, we have impermeable membranes that don't let anything in, no matter what. And then in the middle, we have selectively permeable membranes. In the cases of this membrane, it lets in lipids and water, but won't let in proteins, ions, or carbohydrates. Selectively permeable membranes select which compounds can move into the cell or which can't move into the cell based upon 2 main characteristics. First, the characteristics of the material itself to pass. Here it's looking at the size of the molecule, electrical charge, molecular shape, lipid solubility, and other factors, maybe recognition-based proteins that are on the cell. 2 are characteristics of the cell membrane itself. Here, we're looking at what lipids and proteins are present in the actual cell membrane to allow different compounds to go through. Also, we're looking at how components are arranged on the cell membrane. This is going to be a sample of how different solutions would diffuse through cell membrane. On the top, we have molecules of a dye with a membrane. Here, the membrane is permeable to it, and so it will cross through until it is equal on the far side. Now, when we have a diffusion of 2 solutions, we're actually looking at how it would diffuse through. We're looking at both solutions moving and diffusing across to where it's equal across both sides. Now, diffusion occurs throughout the body, but is most evident when molecules must move across the cell membrane. Only lipophilic molecules in water can pass through a phospholipid bilayer without assistance, and that is called simple diffusion. There are several principles that apply with regards to simple diffusion across any sort of membrane in the body. One is the rate of diffusion across a membrane is directly proportional to the surface area of the membrane. Here, we actually see some of the inner lining of the small intestine. The small intestine has a large degree of surface area with the villi and microvilli, as well as the different cilia that project off of the villi. So this drastically increases the surface area. The larger the diffusion surface, the more diffusion will occur. The small intestine matches structure to function in response to this principle by exhibiting large numbers of small projections at the surface of cells lining the intestinal lumen cavity, thus increasing rate of diffusion. The second principle is the rate of diffusion across a membrane depends upon the permeability of the membrane to that molecule. With regards to membrane permeability, it was just like we've said before. Size of the actual molecule or what it is, and the different proteins that it actually has. So these are going to be the 2 overall rules that apply when talking about simple diffusion across a membrane. These relationships can be distilled down to the mathematical equation called Fick's law of diffusion. This is the rate of diffusion is proportional to the surface area times concentration gradient times membrane permeability. So we've been talking a lot about different compounds moving across a membrane, but one of the most important compounds to discuss is water. In this case, 2 compartments of this tube are separated by a membrane that is permeable to water, but not to the glucose molecules that are in it. So because of this, water will move from A to B to equal the concentration out on both sides. This movement of water is called osmosis, which is the diffusion of water from a high concentration of water to a low concentration of water. When discussing the movement of water, we're looking at the osmolarity and tonicity of a given solution. Osmolarity is osmotic concentration, the total solute concentration in an aqueous solution. If it is a very high concentrated solution, it is hyperosmotic. If it is a very low concentration of solution, it is hypoosmotic. If it is in the middle, as far as being balanced in a given solution when compared to another solution, this is isoosmotic. Not to be confused with tonicity, tonicity itself is going to be the effect of the osmotic solutions on the cell volume. So we're only concerned with non-penetrating solutes in this case. So making sure that we can separate the differences between the two, osmolarity is going to look at one solution compared to the other, where tonicity is about the effect that the solution has on the other. Looking at tonicity, we have the 3 types as well. Isotonic solutions cause no osmotic flow across a membrane. They are equal in concentration. Hypotonic solutions cause osmotic flow into the cell. This causes a swelling or hemolysis in a red blood cell. Hypo, think get bigger. Oh, much bigger. Hypertonic causes osmotic flow out of the cell, which causes a shriveling or crenation in a lot of cells. Hyper, think Moving around, you're hyper, you're going to be skinnier. Hypo, donut, O, larger. Here we have our different examples of a red blood cell. In the isotonic solution, we have a balance between the inside of the cell and the outside of the cell, so no movement occurs. Whereas we look at hypotonic solution, we have a larger amount of water in the outside solution compared to the inside solution. So water will diffuse inside the cell, making the cell swell up. In a hypertonic solution, we have more water inside of the cell than the outside of the cell. So the water will travel from the inside to the outside of the cell, causing the cell to shrivel up, making it a hypertonic reaction.